In this extra session, we will try to define a discrete state Markov chain in MATLAB. So this is the first MATLAB session in this course. First of all, we need to find a way in which we can define a distribution. MATLAB has a random number generator. This is a function rand that generates uniformly distributed random numbers on the closed interval 0, 1. This is all we need to set up any distribution in MATLAB. So on this basis, we can generate a discrete state Markov chain. The idea is very simple. We will define the states. We will generate a vector of any length of uniformly distributed random numbers, and in the last step we will force each random number into an interval, the length of which describes probability. So simply put, the longer the interval, the higher the probability that the random number falls into the given interval. We will have a distribution vector. So we will describe a three-state Markov chain. So to this end, we need a three-state distribution vector. It can be a row in a Markov matrix. So in the first step, we will build a distribution, and in the second step we will define the Markov chain. So in this case, where the probabilities are 0.2, 0.5, 0.3, there is 0.2 probability of going into state 1 from the given state, if it is taken to be a row in the Markov matrix. There is 0.5 probability of going to state 2, 0.3 probability of going to into state 3. So this is a random process. This is the reason why we need random numbers. The idea is very simple, by which we can force so the idea is very simple, by which we can force each random number into intervals to describe probabilities. If the random number is not higher than 0.2, then we go to state 1. If the random number is not higher than 0.2 plus 0.5, then we go to state 2, else we go to state 3. So this is the general framework which we will try to describe in MATLAB. So this is the logical framework by which we will generate a finite Markov chain. Okay, first let's try to describe the distribution. So let's see how to do this. First, let's define n as the length of the chain. This is the first attempt. So in which state, at this in this state, we are not going to describe a whole full-fledged Markov chain. In the first step, we only define the distribution. We will see how it works, and finally we will describe the Markov chain. Okay, so we have the length of the chain. As a next step, we define the values of the chain. okay, let me be specific. This is the value vector. This is the value vector assigning value to each state. Okay, and now we define the random numbers, which is going to be the heart and soul of this thing. Okay, and here we define a blank vector, which is going to be the Markov vector. So this is the initial Markov chain to overwrite. We need a blank vector to be overwritten. I use the zeros function. You can use the linspace function, for instance, so it's all the same. Okay, and let's pick a starting value for the Markov chain. Actually, at this stage, we don't need this, but I am doing so with an eye to the next step when we define a full-fledged Markov chain. So this is the starting value for the Markov chain. Yep. And let's define the distribution vector. This is the distribution vector we used previously in the example in the previous slide. So I think no, here we say that the first element in the Markov chain is M1. So we are inputting the starting value into the Markov chain. Okay, so this is what we have. Everything is set to define the distribution. Here we can take a section break and we start a for loop. This is the length of the chain, so we go from 2 to n, and we will use the if function. If R1 in the given position, if it is lower than or equal to P1 that describes the probability, if R1 is lower than or equal to, okay, then in our distribution it is supposed to be 1. As if the random number in the appropriate position is lower than or equal, now we are summing up the probabilities. Yep, then the next value in the chain is V2, and else in any other case, there is only one remaining case. The Markov, the next the value of the Markov chain is value 3. And we close the if loop, and we close the for loop. And now we are ready to run this small program. And we have the random numbers, and this is supposed to be the Markov chain. So you can see they change according to the random number. So we are happy to say that it works. So in the next step, we will define the full-fledged Markov chain. Let's see how to do this. Previous part of this programming session, we can use everything. With one exception, we don't need a distribution vector. We need a Markov matrix. So it is a Markov matrix we describe quite randomly. The sum of each row is supposed to be 1, so I'm double checking. Yes, it's correct. And let's run the section. Okay, here we have the Markov matrix which we need. I know you remember, but it's important, so let me emphasize it. Let me emphasize the fact that the Markov matrix describes different probabilities to different states. So depending on the state, the probabilities are different. The probabilities of going to state 1 is different depending on the current state. So if we are in state 1, then we have 0.2 probability of going into state 1. This probability is 0.1 if we are in state 2, and this probability is 0.4 if we are in state 3. So this is the reason why the problem is more complex a bit. So let's take a section break and let's start the for loop. I will show you how I do it. I wouldn't say it's the ultimate, the best, or the only solution. This is a solution that works. Okay, so we started the for loop. So in the next stage, in the next step, we call into play the first row of the Markov matrix. So probabilities in pi's first row. So we are assuming that we are in the first state, so we are going to use the probabilities in the first row of the Markov matrix. Okay, so let's work with these probabilities. If the random number is not higher than this probability or 1i, yes, then the next number in the chain is going to be 1. If the random number falls into the second interval, which can be described as the sum of the first two probabilities, P11, P12, yes, I think it's correct, then the next number in the chain is going to be 2. And if the random number falls into the third interval, then the next number in the chain is going to be 3. We put an end to if function, and we are ready to call into play the second row of the Markov matrix, mi minus 1. If it is 2, then we are referring to the probabilities in pi's second row. Okay, and we start the same game again. So if the random number falls into the first interval, which is described by this probability P21, then the next number in the chain is going to be 1. If the random number falls into oh yeah, it's okay. Yep, I was just double checking. So into this interval, then the next number is going to be 2. And if the random number falls into the third interval, it's going to be 3. And we end to if functions, and we are entering the third case. If it is 3, by which we call into play the probabilities in the third row of the Markov matrix. We do the same if the random number is in the first interval, then the Markov chain, the next number in the Markov chain is going to be 1. If the random number falls into the second interval, which is described by the sum of these two probabilities, then the next number is going to be 2. And finally, if it is in the third interval, the next number in the chain is going to be 3, and we are closing the for loop too. So we are ready to run this short program. Hopefully it's going to work. We have the Markov chain, and if we draw a histogram, which I cannot do, then we would see, oh, here we are. Here is the histogram we can see that probabilities, according to his histogram, is in line with the probabilities. Let me show you. So I will start a section break, and let's find the limit matrix to which the powers of the Markov matrix converge. So this is the limit matrix, each row of which contains the unique invariant probability distribution. So if we have a look at the histogram, let's rerun the program. If we have a look at the histogram, then we can see that this distribution is in line with the unique invariant probability distribution. The frequency of the first state is slightly lower than 0.2. It is exactly 0.243, and it is exactly 564. So yes, the Markov chain works, and the result of running the program is in close line what we can expect on the basis of the unique invariant probability distribution. That's all. So we have a proper Markov chain. Hooray!